All right, so we're into now applying the first law of thermodynamics, dealing with the conservation of energy. And we have energy in different forms and transfer of energy with heat as well as work. But we apply it now to an open system. We've applied it so far to closed systems. What's the difference? You can have mass transfer across the boundary of your system. So mass flow in and out of the system. That's an open system. So first let's talk about flow rates. Think about a pipe. We could talk about the radius r of the pipe or the diameter d of the pipe, true? And we could think about flow going down that pipe. And if the flow, the fluid velocity at any point has the same magnitude of the speed, and it's all actually down the pipe, then we have what we call a uniform velocity profile. If not, you got to think about an average velocity over the cross-sectional area of the pipe. Well, if I take a look at the cross-sectional area of the pipe, I cut it and then turn it and look at it, what does it look like? A circle. And the center line is the center dot, so to speak. And when we have a uniform velocity profile, what that means is I could come in here and say, okay, at this point, at this radius, that location right there, how fast are you going? And then at this location, at this location, at this location. And if it has all the same speed, then it has a uniform velocity profile over that cross-sectional area. It's not a hard concept, pretty easy concept, I hope. So let's do this. What is the area, the cross-sectional area of the pipe in which fluid flow goes across? It's pi r squared, and I remember when I was through high school, everything was radius, 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 and then you get to engineering and it's like all pipes are in diameters. If you say, give me a 2-inch pipe, what is 2-inch telling you? It's nominal diameter. Give me a 10-inch pipe, it's nominal diameter. Not precisely, they have charts that say exactly how big a 2-inch pipe is, but it's approximately that. So if I put it in terms of diameter squared, it would be pi d squared over 4. Pi d squared over 4. I find I use pi d squared over 4 much more often than pi r squared. Okay, so that's that cross-sectional area. And if you then multiply the average velocity times the cross-sectional area, just look at the SI units for a minute. This one has units meters per second. This has units meters squared. What do the SI units come out to be? Meter cubed volume per second. That's a volumetric flow rate. Now, some textbooks will introduce a new symbol. They don't in this textbook, and I'm glad. They'll introduce something like Q or Q dot. Well, we're already using Q, aren't we? So, let's not introduce a new symbol for the volumetric flow rate. Let's just say A times V is the volumetric flow rate. That's our name for the volumetric flow rate. The volumetric flow rate is the product of A times V. If you want to be more precise, it's the cross-sectional area times the average velocity down that pipe. What happens if I don't have a pipe that's circular? I have an elliptical duct. Same thing, got to get the area, got to get the average velocity. How about a rectangular duct? Sure. Same thing, get the area, get the average velocity. Then you could talk about a volumetric flow rate. SI units, meter cubed per second. Now let's talk about the mass flow rate. How do I move from a volumetric flow rate to a mass flow rate? So the mass flow rate would be rho times AV, would it not? Check out the units. Meter cubed per second times rho, kilograms per meter cubed. Isn't it kilogram per second then, SI unit? So rho, what is rho again? Mass density times AV, the volumetric flow rate. Sometimes we learned, well, in this class, we learned the reciprocal of rho, the specific volume. I know it's hard to get used to that new term, the specific volume, compared to the mass density, but it would be AV divided by the specific volume. The volumetric flow rate divided by the specific volume gives us the mass flow rate. So you'll see that 1 over V showing up for the mass flow rate. And the meters cubed per kilogram. And so the units work out m dots kilogram per second. Okay? All right. We have a control volume, and we could have multiple inlets and outlets. So for an open system analysis, we introduce a control volume. It's typically a fixed region in space. How do we distinguish that control volume from what's not inside the control volume? Well, we have a clearly defined boundary. And we often use a dashed line that encloses that volume. And so that's our control volume. Here we're going to have a pipe showing flow in. Maybe with the arrow shows us the direction of the flow in that pipe. Maybe this one's showing it's flowing out. Maybe this one's flowing in, and maybe this one's flowing out. True? So for this problem, we have 2 inlet, 2 outlet flow rates. And we could talk about the mass flow rate coming in. Let's call this one inlet 1. We'd say, oh, the m dot 1 is 10 kilograms per second. And m dot 2 is an exit, and because we already know the direction of the flow, we won't put a negative sign on it. We'll just say it's 5 kilograms per second. Something like that. I'm making up some numbers. And then m dot 3 is an inlet, and maybe it's 5 kilograms per second. And m dot 4 is an outlet flow, and maybe it's 10 kilograms per second. For that configuration, what is the mass and the control volume as a function of time doing? Is it increasing? No, it's not changing at all. For every second, the net inflow is equal to the net outflow. True? Okay, let's change it up. We drop this one to, I don't know, let's do 8 kilograms per second outflow. Talk a little bit about the mass in the control volume as a function of time. Let's say it starts there at time 0. Is it going to stay constant? Is it going to go up with time or go down with time? Because this is an 8, we reduced it. The net outflow has been reduced. And so the inflow is 10 and 5, a 15 kilogram per second inflow. And the outflow is 8 plus 5, only 13 kilograms out. So this would be an accumulation. What happens if it was, 12 kilograms per second? The net outflow is greater than the net inflow. This is the rate of change of the mass in the control volume with respect to time, isn't it? The slope. So the rate of change of the mass in the control volume equals the mass flow rates all coming in. Why do we use the subscript I? In. Why do we put a dot over that M? It's not just mass in, but it's the rate at which mass is flowing in, so it's like kilograms per second. If we have multiple inlet pipes into the control volume, what do we put right there? Sum over all the ins. Why do we put a subtraction right there? Because we want to talk about positive mass flow rates out, and the sign we handle by putting a negative on the exiting flow rates. Guess what that is? Conservation of mass for the control volume. A mass balance statement. And this time, well, we often forget about this because it's so easy, right? But sometimes we have to deal with it. We have to work with that equation, okay? So this is our conservation of mass statement for a control volume. We have a 500-liter tank. It contains the two-phase liquid vapor mixture of water at a temperature of 200 degrees C and a quality of 33%. So I kind of make some sketches because I am trying to figure out all this information as we're given it. So this two-phase mixture of vapor and liquid, in the presence of gravity, the liquid's going to settle to the bottom of the tank and the vapor's to the top of the tank. And we're going to have a little valve up there. And if you open that valve, what comes out? Saturated vapor comes into the valve, or it leaves the tank. That's what's leaving the tank. What happens right after it drops the pressure in the valve, we'll talk about that later, it's a throttling process. But what leaves the tank, what leaves this tank is saturated vapor. And we can talk, okay, what is the volume of this tank? Oh, it's 0.5 meter cubed. Let me put 0.5 meter cubed. Did I do that conversion from liter to meter cubed correctly? Yep, good. And then we'll talk about the initial temperature is 200 degrees C. Can you tell me what the initial pressure is? Saturation pressure at that temperature, exactly right. So we could look it up, and it comes in, and I forget what, about 15? I forgot to write it down. Let me look it up real quick. At 200 degrees C, 15.54 bar. That's the pressure of the vapor, the pressure of the liquid. It's the pressure of the contents inside the tank. It's the saturation pressure because it's in thermal equilibrium. It's the same temperature, liquid vapor. All right. Then we have the quality. What was the quality initially? 33%. Now the valve at the top of the tank is open and saturated vapor flows out at a constant flow rate of 0.005 kilograms per second. So maybe I think about m dot E equal to 0.005 kilogram per second. Why do I put the dot on the m? It's a mass flow rate. Why do I put a subscript E? Because it's exiting. What's it exiting? The tank. The tank is my natural control volume for this system. It's a constant flow rate over a time period. During the steam removal, a heater in the bottom of the tank maintains the temperature at 200 degrees C. So we conceptually think of, oh, there's a little electric heater there. It keeps it at 200 degrees C. So after a while, the valve closes. Okay, so maybe I sketch over here, and maybe I think about initial state 1, final state 2. I probably still have some vapor in there. Maybe I color code it like I did before. Some vapor in there, maybe some liquid in there. I still have my heater. It was running the whole time. The valve closes when 33% of the initial mass of the steam has left the tank. All right. So I could think about the mass in the tank at state 1. I don't know it. But I could talk about the mass in the tank at state 2. How is it related to the mass in the tank at state 1? So if 30% of the valve closes when 30% of the initial mass leaves the tank, so it's 0.70 times M1. True? Or maybe the subscripting you want to put for this, you say MCV1. What do you mean by CV1? The mass in that control volume defined it to be the tank at the initial state 1. And then you say MCV2, the mass that's in the tank at state 2. That control volume is my tank. And then MCV1, either way, either you put the CV or you just know, hey, that's the mass in the control volume. All right. What is the mass of the liquid initially in the tank? That's our question that we're going to ask. What is the mass? I have to introduce some notation for it. The mass of the liquid initially in the tank. Is it like m dot or m without a dot? No dot. No dot. Got it? Just m. I like some subscripts for that m. The MLIQ, comma, CV1. I know it's long, but we're kind of clear about that, aren't we? So it's the mass total or the mass that's liquid in the tank? Only the liquid. Only the liquid, true? Yes, sir.
Yeah, so I had a question about the MCV2 you got equals 0.70.
Uh-huh.
Right? Isn't that just of the steam though?
No. It's the way you read that, it's when 30% of the initial mass of the water, maybe I should not use steam, say H2O, meaning both liquid and vapor in it. Okay? Yeah, you don't want to interpret that as the mass of vapor only. Because what's happening during the process, let me ask this question. Is the size of the tank is rigid, it's not changing. But is the volume occupied by the vapor increasing or decreasing as we let some saturated vapor out of the system? And then you ask the same thing. How about the liquid? Is the volume occupied by the liquid, which is at the bottom of the tank in the fluence of gravity, is that going up or down with time? Down. And so what's happening is that heater's turning some liquid into vapor. The heater's on and it's turning some liquid into vapor, and then it's throwing some of that vapor out through the open valve. So the liquid level goes down. The volume that the vapor occupies goes up, and the volume that the liquid occupies in the tank goes down. Make sense? All right. So now what we want to do is we want to find this thing. Again, it's the mass of the liquid that's initially in that tank. Well, let's break it down and think about this for a minute. If I could get the mass that's initially in the tank, if I could solve for this one, how could I then use that information to solve for this unknown? Is the mass that's in the liquid, is it equal to, here, let's help this. What is the definition of quality? Mass of the vapor initially in the tank divided by the mass total in the tank, true? All right. What's 1 minus the quality? The mass liquid in the tank initial divided by mass total in the tank, true? It's either liquid or vapor. If it's 33% vapor by mass, then it's 67% by liquid by mass. Yeah, true? So 1 minus x. And so this is really what I'm looking for, aren't I? And I know the quality initially. So the mass, what I'm looking for is going to be the product of 1 minus the initial quality times the mass total in the tank to start with. Good? How do I get the mass total in the tank that I start with? If I get V initial, how do I calculate it? V sub F plus quality, V sub G minus V sub F. True? What is V sub F? Saturated liquid specific volume. V sub G, saturated vapor. I get it out of the tables at 200 degrees C, out of table A2. In the interest of space, I'm just going to say V1 comes in at 0.04282 meters cubed per kilogram. True? Then I take and multiply by 1 minus x times that value. And so in the interest of space, the mass of the liquid initially in the control volume or inside my tank comes in at 7.824 kilograms. Oh, I forgot. I needed to give you the mass that's in the control volume. That's going to be the volume 1 divided by the specific volume 1. So the mass in the control volume comes in at 11.678 kilograms, an intermediate step. And that's what I put right there, 11.678 kilogram. True? Did I lose you? Okay, good. Stay with me. Now, what about part B? How long is the valve open? Well, let's do this. Let's go back and say for that control volume, I know I've shown the control volume twice. You don't have to do it that way, but initial and final state of the control volume. What we can do is we could say we have a mass balance, the mass balance equation. which says the rate of change of mass in the control volume with respect to time is equal to the rate at which it's flowing in minus the rate at which it's flowing out. Is there any inflow? No, but there's one outflow. And while the valve is open, I know that one. This is given to us right there, 0.005 kilograms per second. True? So basically you separate, integrate, if you like that. And so what we'll do is we'll say the change in the mass in the control volume equal to minus m dot exit dt. When you integrate, that's a constant. It goes outside the integral. You integrate, we'll have the mass in the control volume, the final, minus the mass in a control volume initial is equal to minus the constant exiting flow rate times the time that the valve was opened. And that's what I want to find. I want to find that time, how long is the valve open? This may be beating it with too big of a hammer, right? You know, it's like, wow, this is pretty simple. And do you have to really go and apply these principles of calculus? Probably not. But let's just finish it out. So the time is going to be the initial volume minus the initial mass minus the final mass. Did I switch it? Yeah. Divided by the mass flow rate exiting. All right, we found the initial mass to be 11.678 kilograms. What's the final mass in the control volume? 0.7 times that. And so you either do the 0.7 times that, or you say that this is 0.3 times the initial mass in the control volume. That's what left, divided by the rate at which it left. And you calculate the time to be 701 seconds. Well, what I'm going to do is I'm going to go ahead and stop, and then we're going to hand out the exams and we'll go through them.